Okay, so thanks for the invitation. And if you don't know what any of these words mean, well, hopefully you probably know what a cylinder is, but let's try to get past what a cylinder is at the end of 15 minutes. Okay, so what is a contact manifold? So a contact structure, C on a 2n minus 1-dimensional manifold, is a maximally non-integrable hyperplane distribution. And if you're going back to what you learned in differential geometry at the beginning of your graduate studies, an integrable hyperplane distribution means that at every point you can find a lower dimensional submanifold whose tangent space agrees with the distribution. So something that's maximally non-integrable, if we were working in dimension 3, would mean that nowhere can we find a piece of a surface whose tangent planes agree with the distribution. So here is a picture of such a thing. And of course, this is supposed to be a smooth distribution, so you can't just like sort of throw tangent planes at random everywhere. And in terms of like being a contact geometer, it's like really awesome that we have this notion of a contact structure being maximally non-integrable, but of course, how are you going to detect whether or not this distribution you've written down is maximally non-integrable, and how can you describe it in a more compact way than showing some crazy picture? So the answer is that we can describe it as the kernel of a 1 form, and the kernel of a 1 form is going to be a contact structure whenever it wedge d alpha to the n minus 1 is a volume form, or d alpha restricted to C is non-degenerate. And these these are two equivalent conditions, and it follows by a fairly basic differential geometry exercise. All right, so this is maybe a more useful illustration of what's going on here, but less cool looking. And in both of these cases, the contact structure is given by dz minus y dx. And of course, if you do alpha wedge d alpha, you get everyone's favorite contact structure in R3, which is dx dy dz. So at least we know that that's an example of a contact structure. Okay, and so I guess on this previous slide, this alpha, when it satisfies one of these conditions, meaning that the kernel of it gives you a contact structure, we're going to call that a contact form. And when we do have a contact form, we're going to be able to find something called the Rabe flow. So the Rabe vector field is a vector field that's uniquely determined by these two equations. So the first equation tells us it's some sort of a normalization condition, and the second equation basically says that the Rabe vector field points in the unique null direction of the contact distribution, because if we remember, d alpha restricted to the contact distribution has to be non-degenerate, so there's going to be a direction in which it's 0, and that's going to be in the Rabe direction. And you don't really want to like go back to thinking about what's going on in R2n and thinking d alpha is just kind of like an inner product, because the Rabe vector field won't always point in the normal direction to the hyperplane distribution. In the case of S3 it does, but that's because of some magic things with several complex variables that I can't get into. And if you take the standard contact form on S3, so here U and V are complex, and you think of S3 as sitting inside of C2 as just a hypersurface, then this here is an example of the Rabe flow, and it's actually just going to be the Hopf fibers of S3, which is a fairly basic exercise to do. So Patrick Massot has beautiful images. These fuchsia planes are the contact distribution, and the Rabe flow is this dark purple stuff, and here you can see it agrees with the normal direction of the plane, but that's basically because the standard almost complex structure on C2, when you plug it into d alpha, is going to give you just the standard inner product on Cn. But anyways. And then this is a really nice guy, Niles Johnson. He's a mathematician. He has this beautiful visualization of the Hopf vibration using magma. So if you're bored for the rest of the talk, you can, of course, check this out. But basically, the idea is here's your S2, and then over every single point in S2, you have a fiber of the Hopf vibration, and then the colors correspond to which point you're over S2. So that's kind of a nice visualization. All right, so now we want to talk about this homology business. So the first thing we're going to do is try to pretend like we're doing Morse theory. So we're going to start with a closed contact manifold, and alpha is a non-degenerate contact form, and then we're going to do Morse theory on some weirdo action functional. So the action functional we have is just the space of loops sent to the integral of the loop we're going to integrate the contact form around the loop. And then a fairly straightforward proposition is that this loop is going to be a critical point of this action functional if and only if gamma is a closed Rabe orbit. So then this starts to kind of smell like Morse theory because we have some critical points, and now we want them to be Rabe orbits, and now maybe we can cook up some invariant of this contact form and then we can cook up something that depends on this contact form but prove it's invariant, and then we'd have an invariance of the contact structure, which would be useful. And as far as some technical details, let me just say that the gradient on the orbits is given by the Conley-Zander index, which is basically a complicated winding number that you can associate to any path of symplectic matrices. You get the path of symplectic matrices by linearizing the flow of the Rabe vector field along the closed Rabe orbit, restricted to the contact distribution. And then the chain complex is going to be the set of closed Rabe orbits, and you're going to throw out something called bad Rabe orbits, which is basically going to be orbits that don't have a nice behavior of Conley-Zander index, and magically this works out. Basically, this bad behavior is that there's two different ways the Conley-Zander index can behave under iteration. So when you iterate your Rabe orbit, either the parity of the Conley-Zander index can stay the same, or it can flip back and forth between being odd and even, in which case you're going to throw out all the even multiple covers of the iterates which have changing Conley-Zander index. All right, so that already probably seems like not the best dream in the world, but we're going to run with it because why not? So of course, unlike Hamiltonian Floer theory, when you look at the gradient flow lines of this action functional, you get something that kind of makes sense. In this case, it makes no sense, but that's okay. We're going to use something instead called a finite energy pseudo-holomorphic cylinder, and these are going to be infinite cylinders that limit on closed Rabe orbits. It's a pseudo-holomorphic curve because this J twiddle that we're putting on the symplectization of the contact manifold is not going to be integrable, not in the sense of a contact distribution, but in the sense of several complex variables and complex manifolds. So this is just the standard d-bar equation. And then we want these cylinders to limit on closed periodic Rabe orbits. So this is just the standard way to write this down. So I broke up my curve into components A and F. The A component lives in the R piece of the target, and we want it to go off to plus and minus infinity as our S goes off to plus or minus infinity. And then in the M component of our target, as we limit to plus or minus infinity, we want to be limiting on these Rabe orbits with also the period taken into account. And then also everything is up to reparametrization, which is going to make things really funky later on, because we just care about the images of the Rabe orbits, so we're not parametrizing them. And as a result, we have a lot of actions working on this space of solutions, so things are going to be a little bit dicey because we're going to have multiply covered curves running around, and we'll get to that in just a sec. And then the differential is going to decrease this grading that I've said some vague things about. It's going to be a weighted count of pseudo-holomorphic cylinders up to reparametrization. It's going to be weighted because, unlike in Hamiltonian Floer theory, you only look at time one periodic orbits. But here, my chain complex consists of all of the periodic orbits and all of their iterates, and it's just a big fun mess. And so it becomes a weighted count because we have to take into account the multiplicities of the cylinders and also the multiplicity of the orbits and divide by them so that we have a nice gluing theorem and to show that d squared equals 0. Right? And that also kind of should make you a little bit afraid whenever you see that the differential is a weighted count of things and not an honest count. And then at the end of the day, we're going to hope that this is independent of our choice of contact form and also of this almost complex structure that we threw on the symplectization, which I didn't define for you. And then a very celebrated congerum of Eliashberg, Giventhal, and Hofer from 2000 was that if we assumed a very minimal amount of things, this chain complex is a thing, meaning d squared is 0, and also that the homology is independent of alpha and j. Unfortunately, Helmut is not here to defend himself, but I must give him credit. He actually believed this was a conjecture, and for the last 15 years, he's been working on polyfolds. And at the end of his polyfold project, this can be upgraded to a theorem. But unfortunately, there were a lot of people that did not really read the fine print and went on and proved some really amazing results, which relied on this congerum being true. So it's always not the best thing in the world to do, but it's been around since 2000, so it must be true. Right, and the other thing I should say is that Helmut, Vysotsky, and Zander have many beautiful results about finite energy curves. And this kind of made people all excited to do Morse theory, and they got a little bit ahead of themselves because, of course, in Morse theory, everything is finite dimensional. It's a beautiful picture, and why wouldn't you want to try to do that in this wonderful infinite dimensional world of pseudo-holomorphic curves and moduli spaces? All right, so what goes wrong? Well, there's this thing called transversality for multiply covered curves, and it's not really going to work out so awesome when you have multiply covered curves. So in the standard symplectic topology world, a lot of times you can get transversality by arranging for things to be generic, such as your complex structure. But that really only works when your curves are somewhere injective. And multiply covered curves are not somewhere injective, so things are going to get a little bit dicey. And if we don't have transversality, meaning that the d-bar equation that I wrote down, if linearization of that is not surjective, then we say the thing is not cut out transversely, which means that this moduli space of solutions, like really those of you in the audience that have never seen this before, have just as much idea of what it is as the symplectic topologists do. So we'd really like this to be a manifold or an orbifold, and then that's going to let us to mimic this more serious sort of stuff. But if we don't have transversality, then we're kind of out of luck. All right, so if we don't have transversality, then this moduli space is not a manifold, which means that elements of it can have negative index and still exist, meaning that this moduli space could have non-positive virtual dimension. And this means if we try to compactify an index 2 cylinder, which is the analog of an index 2 gradient flow line, it's going to be like really, really awful. So this is, of course, what we'd like. If we went back to Moore's theory, the index between x and z is 2. And we want to show that to compactify the space of index 2 flow lines, we just need to include once broken flow lines where y has index 1 less than x and also index 1 more than z. All right, so that looks beautiful. Of course, a cylinder would do this. Why wouldn't it? Well, actually, there's a maximum principle, which means that the cylinder can't develop maximum in the R component, but it can develop minima in the R component. Which means that in order to compactify an index 2 or any sort of index cylinder, you have to include all these sort of configurations like this, so that at the end of the day, when you sort of glue everything together, it just has to be homotopic to a cylinder. And if these bits start to have non-positive virtual dimension, then adding 2 to 2 becomes a lot harder than just saying 1 plus 1 equals 2. So then we can have 0 plus 3 plus -1 plus 2 plus -5 plus whatever the numbers on these two things to add to 2 is, and we're not going to be able to prove d squared equals 0. All right, so why would you maybe think that this was worthwhile to pursue? Well, you wouldn't because you were a graduate student that was too naive to realize that there were all these problems, but along the way you started to read some things and notice that in dimension 3, Wendell, Hutchings, and Taubes have really nice automatic transversality results. And I don't really have time to go into this, but the moral of the story in symplectic topology is that pseudo-holomorphic curves just work better in dimensions 3 and 4. As a result, you can get these automatic transversality things by basically computing topological quantities associated to the curve, including things like the first Chern number and what the Conley-Zander index does. And you can also use Riemann-Horowitz to understand what the index would have to be of multiply covered curves when you combine it with results of Micallef-White on the asymptotics of curves. And then, so you work backwards from your thesis, which was to come up with a way to compute contact homology and realize that actually the perturbation you came up with allows you to achieve transversality for a more limited class of contact forms. Okay, so the definition that I came up with in a reverse way is that we're going to work with dynamically separated contact forms. This is going to be in dimension 3. We're going to assume the first Chern class of the contact distribution is 0, so there's a well-defined integral grading coming from the Conley-Zander index. And then this works when you have more than just contractible Rabe orbits, but the definition is harder to explain, and I only have like 5 minutes left, so we're not going to go into that. 1 minute left. Okay. So the basic thing is all closed simple contractible Rabe orbits satisfy Conley-Zander index between 3 and 5, and every time we iterate the Rabe orbit, we want to go up uniformly by 4. And then the theorem is that d squared is 0, and you get invariance under the choice of j, but only under dynamically separated alpha. So it's not going to be for all contact forms. So then we want to, of course, upgrade this and get to a bigger class of contact forms. So we're going to do more index calculations, we're going to do more intersection theory, and we're going to team up with Hutchings because he's smart and knows things. And then we're going to prove that the remaining obstruction to d squared equals 0 can be excluded. So this is actually the only building of index 2 in a 4-dimensional symplectization that's going to prevent you from proving d squared equals 0. And this we can get rid of with intersection theory. as long as we assume that we're working with a non-degenerate dynamically convex contact form, which means that every contractible Grabe orbit satisfies Conley-Zander index greater than or equal to 3. These, of course, exist a lot in nature. Any convex hypersurface that's transverse to a radial vector field in R4 will admit a dynamically convex contact form. And then our theorem is that d squared is going to be 0 in this case. All right, so then we're still stuck in invariance, and since I only have 1 minute left, we basically throw everything that we possibly can at it. So there's non-equivariant formulations, domain-dependent almost complex structures, obstruction, bundling, gluing, family Floer homology constructions, and at the end of the day, you do a lot of stuff. You tensor the thing you wrote down with Q, and you can see that you get back regular cylindrical contact homology, and this gives us invariance. And I'm done. All right.